Hey there, welcome back to Short Text 331. Today we're going to continue talking about generalizations and applications of Fourier series. And this is part 3, so if you haven't seen part 1 and 2, you might want to check them out right now. So from part 2, if you recall, we ended up with a solution for a spherical diffusion problem, and we left unsolved the part of figuring out the radial dependence of the problem. And this came from trying to use eigenfunctions of the Laplacian operator of this generalized second derivative in spherical coordinates. And we said, well, this Laplacian has a radial part, a purely radial part, and it has an angular part that depends on derivatives on theta and phi only. And there's this 1 over r squared here, of course, but this derivative only acts on theta and phi. And it turns out that for this part of the problem, we can use spherical harmonics. And these spherical harmonics are objects that we haven't discussed too much in these videos. But if you look at previous videos that were mentioned before, but we'll probably do a future video with more information on that. What you need to know right now is these are functions that depend on theta and phi, these spherical coordinates in 3 dimensions. And when you apply that angular part of the Laplacian, you get minus L times L plus 1 times the same function. So they're eigenfunctions of this angular part of the Laplacian. And this L plus 1 is of course just an integer, and L starts at 0 and goes from 0 to infinity, and they're all integers. Now that solves for the angular part of the problem, but we're still missing this radial part. And if you take this proposal for these eigenfunctions of the Laplacian and you put it into this equation, then you'll find that you can derive, and you can see that in the previous video, you can derive an equation for the radial part that looks like this. And here we replace lambda for minus k squared. We have an argument why we only care about negative values of lambda given the exponential dependence of the solution with respect to time. And so we put a minus sign there, and k is something that we haven't figured out what it is yet. Now, something I didn't mention in the previous video is that these Rn functions, aside from depending on this differential equation and these boundary conditions, well, you see here actually that in the differential equation we have this L times L plus 1 eigenvalue of coming from the spherical harmonics, and that means that this solution will depend on L. And so we actually should be adding an index here that I'm going to add first to the r's. So these r's are going to be functions that depend on some index n, which we haven't figured out what it is yet. It will come from enforcing these boundary conditions. And it will also have an L coming from this L of the spherical harmonics. So we'll just call them RLN then. And we're interested in a solution to this second order ordinary differential equation with this boundary condition that it vanishes at radius r0, which is given by the problem. And then, but other than that, we're interested in this region where r goes from 0 to r0. This is if you want the interior problem. We could be interested in other situations in the exterior problem, where the problem starts at r0 and goes to infinity. That's something else one can do as well, with a very similar setup, of course. In fact, pretty much identical, except that we have to change the region, and then the problem gets a little richer. And we can talk about that in a future video as well. Now, something that you can figure out right away from this equation is what happens close to the origin. So close to the origin, there are some things you can throw away when you look at all these terms. So these terms here involve the derivatives of Rn. There will be a first derivative term, there will be a second derivative term of Rn, but these terms involve Rn itself. And they scale differently with the radial coordinate. And so when r goes to 0, this term will necessarily become much more important than this one. And so if you throw this one away, as r go to 0, you get a much simpler equation, which you can solve with a single monomial, it turns out. So if you propose for this simplified equation, you propose r of r is a constant times r to the m, then you can take this second derivatives and figure out that what you obtain is a very simple equation, which tells you two things could happen. Either this power m is L, this integer coming from the spherical harmonics, or is minus L minus 1. Now, at the origin, we don't think that the solution should be singular in any way. So since L is a positive number, then either it could be 0 or a positive number. So it's definitely not a negative number. So it's not negative. Then we have to pick this type of solution here, m equals L. So we cannot have the other one, m equals to minus L minus 1, because this would be singular at the origin, and there's no reason for us to believe that the solution should be singular at the origin in this case that we're studying. So this tells us something, that it's in fact independent of whatever k is. So no matter what solution we're looking at, if we know L, then it has to satisfy that at short distances, when we approach the origin, it has to go like r to the L. So that's an interesting thing to know, and it gives us a little bit of a handle on checking if we have the right solution. But we still need to solve the more general problem. And so to that end, we go ahead and we rewrite our equation by multiplying by r squared. So let me go back up. So here we take this equation, and we don't like this r squared down here, we don't like this r here. So we multiply across by r squared, and we write this equation for r, for big R, in this way. And it turns out that the solution to this equation has been studied. In fact, when you see an equation of this form, which has second derivatives only, and it's linear in what you're looking for, it's linear in your unknown, and otherwise there's nothing strange. So second order ordinary differential equation and linear, those have typically all been studied. Although perhaps you can come up with a case that hasn't been studied, but the majority of these that are interesting for physics have been studied, and they're known very well. And so in this case, the solution to this problem is what's called the spherical Bessel functions. And let's talk a little bit about those, but you can look them up. And they have an index that corresponds to this number L here. And so they're denoted by J and then sub L corresponding to this parameter L in the equation, again coming from the spherical harmonics. And in our case, in fact, this kr here, this k will appear here. So this k squared r squared tells us that this JL is a function of k times r. One way to think about this is that where does r appear? Well, it appears here, it appears here, 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 and this little r doesn't appear as a variable really here, except as a function in terms of big R, as a variable for big R. And so if you take this part of the equation, you multiply and divide by k squared, you can attach a k to this, and a k to this, and a k squared to the second derivative. And so in reality, the variable we're playing with in this equation is really kr. And so that's why this appears as a function of kr. And we'll see that that's very useful for us. There are other solutions to spherical Bessel functions that are linearly independent from this one here, from the j's. They're called the y's sub L, kr, unrelated to the spherical harmonics, by the way. And nothing to do with that. It's just notation y sub L. But these ones are singular at the origin, and so we don't want those. We keep the regular ones. And that's as much information as we're going to extract from keeping the regular solutions at the origin. Now we still need to enforce that our solution has to vanish at r equal to r0. So we want to use this as a solution to our problem, but we had to adjust k. Remember that k comes from the eigenvalue lambda, and we haven't really figured out what that is yet. And so that is enforced by our boundary condition. And so in this case, what we want to say is that we want to take xln to be the nth root of jl of x. So we want to make sure that when r is equal to r0, this input into the function makes the whole function vanish. And so if we're considering jl of x, then it will be a function that typically will have this type of shape. Actually, this would be for j0. If you were to have j1 or j2 or higher j's, then they go to 0 at the origin. This one goes to 1 here. But they all have roots. They all have a sequence of roots that go all the way to infinity, it turns out. And so then this function, that's a function of x, will have n will have a sequence of roots, and so we can parameterize those with an n here. And so jl will have multiple roots that will denote xln. And so that's why we want to write our k's now as kln's. So this variable k, which again comes from the eigenvalue, is going to have two indices now, kln, depending on which L we're talking about, which root we're talking about. And that specifies, that's given by xln divided by r0. And so we'll see how that plays out then, because our final solution for rln of r will be j sub L of kln times r. And so why this combination? Because then in that form, well, first of all, that's the solution to the differential equation. It has to have a kr there. But also, if we pick kln as the nth root of the L spherical Bessel function divided by r0, then that means that this function is actually this. And so when r is equal to r0, then these two things cancel. We get 1 here, and then we get the function evaluated at the root, which will be 0 as we want when r is equal to r0. So that is really how the boundary conditions then enforce that we have to pick those roots, and then it quantizes the possible solutions. So that's why the n, which we didn't know what it was, the little n here, is actually indexing those roots, of which there's a discrete number that goes from 1 to infinity. And so to give you an idea of what the roots do, it turns out that for L equal to 0, if we were to pick the solution that has L equal to 0, then the roots look like this. x0, 1 is pi. So this first, if we were plotting here j0, which is sort of what it looks like this, turns out, then this one would be pi, this will be 2 pi and 3 pi and so on and so forth. Now, if you pick L equals to 1, there will be actually a 0 down here, which we want to ignore. I'll tell you about that in a minute. But then the next one, there will be an x11, it will be a 4.49 and so on and so forth. This could be computed very precisely if you want. And you can use bisection, as I discussed in a previous video, if you want to calculate this root very precisely. And then x12 would be 7.72 and so on and so forth. And there will be multiple roots all the way to infinity you can calculate. Now, for L greater than 0, L equals 1, 2, and so on, there will be a 0 at the origin. But you really don't want to pick that up. Because if you take that root, then what you will see is that this k will be 0. If you pick the x equals 0, then k will be 0. So this whole combination will be 0, and the whole function will be 0, and the whole solution will vanish. And we really don't want that kind of solution. That's not a proper eigenfunction of our operator. Eigenfunctions cannot be entirely vanishing, and so we discard those as not what we're looking for. It's not interesting. It doesn't do us any good. It really doesn't help us at all to solve our problem. If you recognize that this was pi and 2 pi and so on, that comes from the sign of x, then that's indeed actually what happens. The 0th spherical Bessel function is actually sine of x over x. The first spherical Bessel function is sine x minus x cosine x divided by x squared. And it turns out that there's this general formula for the spherical Bessel function. So if you start with this one, sine of x over x, then you can take L derivatives to obtain the Lth spherical Bessel function, then divided by x L times as well as you go taking derivatives, and then multiply by minus x to the L. And if you look at this, you recognize what we discussed before, that there's something here about that dependence at the origin of the functions. Our solutions having to go like r to the m when m is equal to L. So when L is equal to 0, then we just go to a constant, but when m is equal to 1, 2, and 3, and so on, then our function vanishes at the origin as some power of the variable r, which is indeed what happens when you look at all these solutions. So now recall our objectives. So this whole song and dance, of course, was to complete our discussion of finding the radial part of the problem and how that imposed the quantization of the eigenvalues of the Laplacian operator. So once we have that, so then we have this radial part of our solution to the diffusion equation. So this is where this whole thing came from. We wanted to solve the diffusion equation, and so this is our solution, which we wrote only formally. Here are initial conditions, this is our time dependence, then our radial part, which we just discussed, and then the spherical, the angular dependence given by the spherical harmonics. And now we have zeroed in on what exactly the eigenvalues are. These eigenvalues lambda n are the minus kln, that is minus the nth root of the Lth spherical Bessel function divided by the radius of the sphere that is in our problem. So that's how all the geometry enters into this game. Now, we assume that we're given the initial shape. Of course, we assume that these constants are given to us. And if you put t equals to 0 here, you see that this initial shape, which on the left-hand side is something that is given to us in terms of numbers or some function or whatever it is that is given to us. Now we had to expand it in terms of our spherical harmonics and our radial functions, which we just found, the spherical Bessel functions, and some constants that we have to figure out in order to feed them into our solution and then figure out the time dependence. Now, suppose we have a spherical symmetric case as an initial condition where all these coefficients Cn of 0 actually vanish, and for all L greater than 0. So we only have L equal to 0, which is the fully spherically symmetric one. And for L greater than 0, it will have some more complicated shapes. But if we only keep the L equal to 0, then we'll be spherically symmetric. In that case, the little m here can only take the value 0. And for further simplicity of discussing this example, we're going to take n equals to 1 to be the only non-vanishing case of z, and we're going to kill all the other n's for n greater than 1. So we're going to assume that all these constants are 0 except the one n equals 1. And that case is extremely simple. That means only one term survives in this sum, the term that is given by r10. And so that f of r comma 0, so at 0 time, at t equals 0, we have just the r10 contribution, which is the 0th order spherical Bessel function, the first order spherical Bessel function. And no, actually, I'm right. It's the 0. This should be 0, 1. So it's the 0th order spherical Bessel function with n equals 1. So it should say 0, 1 here. And so that gives a sine of pi r over r0 divided by r over r0. So this pi divided by r0 is, of course, our variable k that we discussed up here. So this is the pi over r0 is all we have, and so that's what goes here. There should be a pi also here, and so that then is our initial condition. We're assuming that's our initial condition, and so in that case, then we have that the time dependence is basically given by this function. Again, fixing that I'm missing a pi here, and fixing the indices here. But then we have an exponential decay coming from e to the minus d. This d is some diffusion constant that's given to us. There's a pi over r0, which is our eigenvalue, with the minus sign. Actually, it's the eigenvalue, and then times time. So this is a decaying exponential times the initial shape of our problem. So this is pretty much as far as I want to go in discussing this solution. You should plot it. You should play with this by varying n and l and possibly adding more modes to the initial conditions. So here I try to keep it very simple, keep it spherically symmetric, and keep it to only one mode for the radial part. But you could add more modes and play with it. And what you will find is that as you add more and more modes, then the eigenvalue, which is controlled by these roots of the spherical Bessel functions, they go up very quickly. And as they go up, what it means is that in this exponential, in this constant here that appears in the exponential, there will be higher and higher numbers for higher and higher modes. And so those modes will die off very quickly with time. And in the end, if you wait long enough in your in this movie, as you run the movie for higher and higher times, as you plot it as a function of time, you'll see that ultimately the profile that survives for the longest is the one with the lowest eigenvalue. And that's really a big part of the physics behind this. That is that the low modes tend to survive longer on the higher modes, so phi eigenvalues die quicker. And that's about it. That's all I have for you today. I hope you enjoyed this video. If you like this video and this series of videos, consider liking and subscribing. Check out definitely parts 1 and 2 if you want to see really the context of what was discussed here. If you're looking for a tutor in physics or math in English or in Spanish, you can contact me at shorttakes331@gmail.com, or you can leave a message in the comment section below and I'll get back to you. And that's it. I'll see you next time.